All right, so let's start. So today we're going to be talking about chiral anomaly or anomalies. We'll start the discussion of anomalies, and let me say a few words about what anomalies are. Anomalies are classical symmetries that do not become quantum. They fail to become quantum symmetries. Now, how could a classical symmetry fail to be a quantum symmetry? Well, what does quantum mechanics have? If you have a particle propagating from point A to point B, there will be all sorts of paths that you're path integrating over, and you associate. You have an action functional, right? You associate to every path the S over I or e to the power is over h bar, right? So if S is symmetric under the symmetry transformation, it means that the value that you associate to every such path remains the same. So how could a classical symmetry fail to be an integral, to be quantum? Is by this measure. If this measure fails to be invariant, that's the only thing that could happen. Now, if this is like a finite number of integral, it makes no sense for this to fail. It has to be a result of a consequence of the infinite dimensionality of these integrals. So, right, good. Now, when you put the theory on the lattice, what do? You write this down as a bunch of integrals like this, and you cut this off, right? So you turn this into a finite number of integrals. If you put the theory on the lattice, a classical symmetry must become quantum symmetry. So anomalies have to do with theories that could not be put on the lattice. If you have heard this statement, chiral fermions could not be put on a lattice, it's precisely about this statement. So we're going to discuss this in detail today, right? All right. But before doing that, let's start with a review of lecture 22. So we talked about quantization of spontaneous symmetry working gauge theories, the so-called Higgs mechanism. So we saw that in global spontaneous symmetry wrecking, we found gold-sum bosons, which were massless modes. For each, there will be one gold-sum boson, massless bosonic modes for every single generated symmetry, global symmetry that was working. Gauge theory, spontaneous symmetry working ones, there is no gold-sum boson. What the physics of it, we explained as the gauge boson will have to be massless by gauge symmetry, but when you have spontaneous symmetry breaking, the gauge field becomes, the gauge boson becomes massive. The mass of it makes the interaction short range, right? Example of this, and this is consistent with gauge invariance because we discussed where the connection between word identities and the mass came from, right? And if you have massless modes running in the loop, that is consistent with giving a mass to gauge bosons. An example, physical example of this, there are two examples to keep in mind. One is superconductivity, where psi gets a VEV, right? That's one example. So this is a charged boson. Then the other example is the Higgs mechanism. So we talked about the abelian Higgs mechanism. Today I will review the SU2 Higgs mechanism. That's going to be electroweak spontaneous symmetry breaking. It plays an important role in Standard model particle physics. So in anticipation of discussion of Standard model, I'll review that. We did the non-abelian thing pretty fast, right? I'll review it, but in the particular case of SU2, because it's relevant for particle physics. If there are any questions at any points, please ask. So spontaneous symmetry breaking of SU2 gauge theory. Here's the action. Minus half. This is the Yang-Mills term. Here's the covariant term. So the scalar is in a two-dimensional representation of SU2, the fundamental representation. It's a complex scalar with two elements, right? So the transform is a doublet under SU2. And here's the potential. So the gauge boson, there are three of them, labeled by the generators of SU2, which are half of Pauli matrices. The variation of the gauge field, the gauge transformation, will send a mu A to del mu of some function. Gauge transformations are now labeled by the generators of SU2. So there are three functions worth of gauge transformations minus epsilon ABC. What is this? This is these are the structure constants of SU2 in the adjoint representation. W of B, A mu of C. Good? Everybody's with me? All right. So under this transformation, this transformation is a symmetry of the action. Under this transformation, phi of J, the Higgs field, transforms this way. Right? Oh, sorry, I put alpha. This should be omega. Right? And the covariant derivative transforms this way. To repeat in the SU2 gauge theory, this is important because we're going to literally copy this model in Sano model. We are dealing with a complex scalar field. So the Higgs is an SU2 doublet, right? Which is a scalar under Poincare transformations. Right?
Is an SU2 doublet because it has two real parts?
There's no real, it's complex. So it has two components and each component is complex.
Yeah.
These are SU2, fundamental representation of SU2 is a complex two-dimensional vector.
Yeah, but then that affirmation of is an SU2 doublet, we haven't justified it.
It's a model that we start with. It's SU2, it's SU2 gauge theory with a scalar charged under SU2. It transforms on the fundamental of it, right? Scalar means representation Lorentz group, and the fundamental of the gauge, right?
But it's two-dimensional by hand.
I
want it to be.
It's SU2. Yeah, the representation decides your theory. So when I tell you about Stano model, I write the matter content. I write down the symmetries, right? Internal and space-time. Then I have to assign, to define a theory to every field I define. I have to give you what the quantum numbers are. So these are quantum numbers.
Yeah. But it could as well be a four-dimensional representation of this.
What are the representations of EREPs of SU2? What dimensions do they have?
No, three.
So just recall what they represent. Their dimensionality is 2J. Yeah.
2J plus 1J.
Right? So that's EREPs. To call it a particle, you will have to have to call it a field, you will have to take it to be an EREP. Right? Any other questions? All right. So how did it work? Well, we can take the Mexican hat potential, but we don't need to worry about that. We went through that in detail last time. The classical equation of motion will set the gauge field to 0, right? And then we expand around some phi 0j, which is the classical VEV. And chi is now your Higgs field that's fluctuating around this vacuum. In the expansion of the covariant kinetic term for the Higgs, we found this mixing term, right? So this mixing term mixes the non-abelian gauge field, right, with the Higgs, with phi 2, sorry, with phi 2, this is the expression mixes it with the scalar, right? So this is a non-abelian version of this. It's hard to, it mixes it with the would have been a Goldstone boson, right? But there's no, that's not a gauge independent statement. So it's convenient, as we discussed, to use a gauge fixing that removes this mixing term. That is precisely analogous to the gauge fixing term that says phi 2 equals 0. Right? Good. All right. So here's a gauge fixing. We saw that if you plug this in, how do you cancel this term? that when you have this term, it will contribute in the Fediev Popov as e2 minus half GA squared. Sorry, e2 minus, it will contribute as e2 minus 1 over 2c GA squared, right? There will be a cross term here, right? So, yeah. Omega of A, W, A mu A. The cross term will be C order C and then cancels this. It will give you something that is precisely what you need. By tuning omega A, you get to cancel this term, right? All right, with this gauge choice, here's what the Lagrangian is. We saw that, so the gauge dependent mass term for the gold sum, in this particular sigma gauge, when we work, we assign the sigma so to cancel the mixing term, we end up with a gauge dependent mass term for the Goldstone mode, quote unquote Goldstone mode, right? This is all gauge fixed. Now the kinetic term for the gauge field also picks a mass term, which depends on the VEV, right? The gauge boson propagator, we wrote it down this way. And the poles of the propagator, of course, they carry the physical masses, which are the eigenvalues of m squared. So here are what we're an arc-C gauge, so there is still gauge dependence here. There are different choices of gauge that you could choose to write down the propagator of the gauge boson. The unitary gauge, this makes the Goldstone boson mode infinitely massive. That's how it kills it, right? That's how phi 2 was killed in the abelian Higgs model. This is the propagator in that case. Landau gauge is C equal 1. And this is the Feynman gauge is C equal 0 is Landau gauge, so-called transverse. And the Feynman gauge is sigma equal 1. Good. So this is what we discussed last time. Then we talked about the standard Fediev-Popov method, giving us the ghost, right? So we have a gauge fixing, del alpha, right? So I have to take the determinant of this. This is that contributes as a Jacobian to my path integral. In the past, we saw when in the absence of spontaneous symmetry breaking, in the abelian theory, this determinant would become determinant of the Laplacian or the Lambertian in flat space, which is just a constant, infinite, but constant that comes out of the path integral. So we just discarded it. There were no ghosts in the abelian model in QED. However, in the non-abelian case, this determinant ended up being, well, the determinant was replaced by this was replaced by determinant of del mu d mu, which now has an a mu term that you're path integrating over. So you're not allowed to discard this. Ghosts were adjoint scalars that were non-commuting degrees of freedom that we introduced to pull this determinant up inside the action, right? So there was the ghost anti-ghost, they were complex. Now here what happens, and this was a feature in the non-abelian gauge theory, right? Now here what happens, even for the abelian theory, you end up with ghost. The reason is that this is now shifted, right? Because you use gauge fixing, you fix C, right? To cancel that crossing term, right? So this is now, well, in this case, in the non-abelian case, this is the expression you find, right? So the Higgs field appears here. Of course, this is what would have been, this is this term, right? So there is a ghost would talk to the gauge boson, but they also talk to the Higgs, right? In this model, in spontaneous symmetry working case. So here's the ghost action. You could see explicitly that this couples it to the gauge field and this couples it to the Higgs, right? Now this overall shift, is it meaningful? Is this overall shift? This is a shift. There are two terms here.
Yeah.
One of them is a constant that depends on the VEV. What is that? What's the meaning of that term?
Mass.
Mass, and it's gauge dependent mass for the ghost anti-ghost. Good. So here are the Feynman diagrams. It's convenient to define this FAI, right? Which are yeah. So here's a mass matrix. And the propagator for the gauge field could be written in terms of this matrix very efficiently in the RKC gauge. The Higgs boson, similarly, the ghost. Good. All right. Any questions? This was my review of the last lecture.
Yeah, I still don't understand the notation. Tij phi 0j.
Mhm.
How can I read it?
So you're an SU2, right?
Yeah.
What are your matrices? You have three of them. You have T1, T2, T3. What are they? These are sigma matrices. Sigma x, this is T1 up to a constant, right? This is I minus I, and then this is this. So what does it mean to talk about TAIJ,
The ij.
particular matrix element of this?
Okay, and then
And now, what is this acting on? The gauge field. Sorry, it's acting on the fundamental representation of the field, the Higgs. So the Higgs is in a doublet. So when I write TA ij, what did I write? Phi 0j, give phi 01, phi 02, right? Zero here means expectation value, right? Now there is a particular TA that acts on it, and then the result has two components. That's the index I, right? So then when you view it, good.
yes, it's not that in the last lecture you said I'm not thinking, but now it makes more sense.
Right. It's very compact notation. But although if you actually do calculations, like if you expand, you have to expand things this way, right? And then it becomes
Then
manifest.
why do you have F transpose instead of F transpose F?
Here? Ooh, I don't remember. Oh no, that wait a second, sorry. Maybe this is a typo. Yeah, I'll double check this. It should be FF transpose, I think. Yeah, I'll double check that. Oh no. It's not. No. So F transpose is a matrix with AB. So it's a 4x4 matrix, 3x3 matrix in SU2. F transpose F is a number.
Yes.
Okay. So no, and then this is the Higgs. This thing doesn't have AB indices. Good. It has IJ indices. Good. No, that's correct. Yeah, sorry. I think. Of course, the Higgs is transforms as a doublet. So I have to put indices. These are run from 1 to. So these are 2x2 matrices, and these guys are 4x4. Okay. Questions? So now we want to start talking about anomalies this lecture and the next. So we saw that symmetries played a crucial role in the construction of quantum field theories. Noether theorem told us that continuous symmetries resolve in conserved currents. This derivation was fully classical. So in the quantum world, the current becomes an operator. The question is, does this hold? Or could it fail? When this fails, we say we have an anomaly. Actually, it's a little bit loaded. What I'm saying is a little bit loaded. If you recall from QFQ1, and there will be contact terms, right? Every time you try to, actually QFQ1 and I reviewed in QFQ2 as well, when you have a current that's conserved and everything is fine, there will be contact terms. So, right? So there will be, if you stick inside the correlation function that has a bunch of charged operators, insert at x1 to xn, there will be a sum over Dirac delta function of x1 to xn on the right hand side. But that's not what we're talking about. We're talking about an operator, another thing sitting on the right hand side. Good. Anomaly is a symmetry of classical theory which does not survive in quantum theory. Anomalies appear in quantum mechanics, in quantum field theory, in all sorts of models. They could appear anytime the measure of the path integral does not preserve the symmetry. Now, let's go back to quantization. Remember, why did we introduce dim-reg? Because we had symmetries that we wanted to make sure they're preserved, right? Every time you regulate, so it was supposed to be a regulator, dim-reg was a regulator, it's important that you preserve it. Now, over there, I made the comment, if you happen to be working with a theory where there is a symmetry that you could not write down a regulator that preserves it, that theory is anomalous. That means that there exists no way of regulating the path interval, right? Such that it preserves the symmetry, which means that the path integral measure will not be invariant. So we'll do this calculation today and study it and understand it. Now, the example I want you to have in mind is the following statement. You'll hear it a lot from your condensed matter colleagues, that chiral fermions cannot be put on a lattice. Now, that's a complicated statement. Chiral fermion is a fully sensible quantum theory, relativistic invariant quantum theory, and there's absolutely no problem with it's a fact that you cannot put it on a lattice. It's a fact. The issue with the quantum theory, as we'll see today, is that the chiral fermion could not be charged. So we'll see that. All right, so let's talk about global anomaly. We'll talk about global anomaly mostly next lecture. This lecture is about something simpler. Global anomaly is actually more involved. Global anomaly is when you have a global symmetry that's anomalous. For example, Yang-Mills theory is classically scale invariant. The various ways to see it, the simplest way of seeing it is to just notice that you didn't use any mass to write down the action. Everything is dimensionless. G has this dimensionless. Classically, what did we call this? Such a term? Marginal. So the action is marginal. Lambda phi 4 was also marginal, right? Classically. So that's classically, scale invariant, because lambda is dimensionless, but that theory doesn't exist. That's why I didn't give that example. In lower dimension, okay. So this is scale invariance. The conserved current associated with it, if you recall, is this trace of the stress tensor. So this will fail to be promoted to an operator as an operator equation in the Hilbert space. So there will be something sitting on the right hand side. Quantum mechanical symmetry is violated. The example is that the theory is, physically it means that we know that the theory confines that lambda QC beta functions are non-zero. That's the first thing to know. So, but I want to stress this. We'll come back to this, hopefully, and comment on this. Maybe not, actually, won't have it time. That a theory that has scale invariance classically and quantum mechanically fails to have scale invariance must introduce a scale. Quantum mechanically, it must introduce a mass scale. It's just kind of a mind-blowing statement. Such a thing is called dimensional transmutation. Quantum effects should cook up a mass for you. What is this mass? In the case of QCD, it's the confinement mass. We said there's a phase transition, right? As we crank up as we go to low energies, at some point, the energy cost at some finite energy scale as you run towards infrared. At some finite energy scale, you will hit a scale where the energy cost of a quark is infinite. And that's a scale. That's a physical scale. We call that lambda QCD. The theory confines. It's a phase transition. You undergo phase transition. That scale, it's a big challenge. It's a $1 million prize to figure out how to prove that how that comes about. Good.
The price is in pure young years.
What is?
The price is in pure
Oh,
young years.
the formal definition of the problem is in pure Yang mills. Yes. I think we are sure we need brand new ingredients. We need something that we have not quite, mathematically or physically. We're missing an intuition that is so profound that it's not about QCD versus not another SUN theory, something profound. All right, so today what we're going to talk about is chiral anomaly. Good. Now, here the language can get confusing, and I'm genuinely confused about the terminology because there's some sort of a mismatch between what people used to call, what words people used to use and what they use now. There's a modern understanding that's outside of my comfort zone. I'm not an expert on it, but I want you to keep two statements in mind. First is that gauge transformation, gauge theories are gauge transformations are redundancies of the description. They are not real symmetries. So it makes no sense to have an anomalous gauge theory. That's an inconsistency of the theory. Global anomaly just means that the symmetry you thought you have, you don't have it. There's Hilbert space, things are complicated. The theory is still healthy. QCD exists. It's a healthy theory. We just don't, like the symmetry is not healthy to understand it. However, a gauge theory, if it's anomalous, you have to discard that theory at the level of this course. Like that theory is sick. It means that there is no way of regulating the theory in a gauge invariant way, right?
So global anomaly is kind of like a emergent phenomenon in classical sense. Like in quantum theory, we don't have it, but in the classical theory, we can see the same.
Yeah.
But the gauge anomaly is something.
Yeah, gauge anomaly is something just says that if you wrote down a classical action that was gauge invariant, and then you stick it inside the path integral, and there is no measure that preserves it, that's not a quantum theory.
That simply means your theory.
It's garbage. The theory is garbage. Right? Now, those are good. There is another notion, here's where my confusion starts, which we call Tuft anomaly. And it's about a global symmetry that could not be gauged. What is gauging? You have a global theory, global symmetry, and then you pronounce that only the invariant states, singlet states are physical. You project that sector, right? So that's what we're going to be talking about. Keep that in mind, but to be very, very specific, I will be talking about chiral anomaly, which is a symmetry, global symmetry of a chiral fermion that if you make it gauged, it leads to inconsistencies, right? So we're talking about anomalies that arise due to fermions. I'll stick to a particular example, right? Chiral anomaly will be very important. So a theory that has chiral anomaly, it will be important that chiral anomaly with standard molar particle physics will have to cancel. That will be important. Sorry, let me clarify what that is. Maybe I can say it in advance. Yeah, no, let me clarify. So when you say you have when you say chiral, a chiral fermion cannot be regulated, right? On a lattice. Let me try to explain what the physics of it is that we were discussing. We'll see that if you have a charged chiral fermion, just the chiral sector, that's inconsistent. You could have a charged fermion that has the chiral and antichiral mode, but not just a chiral. Particle antiparticle, but not just a particle. It's inconsistent. Classically, it's sensible to just truncate to the chiral mode. But we're going to go through that. But quantum mechanics is inconsistent. Why does this matter for standard model? We'll see in the standard model of particle physics, we're going to assume particles that are chiral. We're going to include in our matter content things that are chiral. If the chiral anomaly, there is chiral anomaly, it means that what we wrote is garbage.
By that, you mean that you take the Dirac fermion data?
I'll go through. So let's talk about QED coupled to massless fermions in 4 dimensions. All right, good. Or any even dimensions. What's the action? Here's the Dirac action. Here's the QED action, the gauge field action, photon action. We're in 4 dimensions. We have gamma 0 to gamma 3, and then what we define gamma 5. Here's gamma 5. Right? This is a 4x4 matrix. The job of it is there will be chiral and antichiral modes, right? So 1 plus minus gamma 5 over 2 projects to the fermion antifermion, to the chiral, left and right, right? All right. So there, because the theory, so for example, imagine your fermion. So now your fermion in 4 dimensions is a 4 vector, but you could bunch it into 2 doublets. Left-handed electron, right-handed electron. The gauge transformations are, so these 2 guys transform independently under gauge transformation. There's 2 function worth of transformations, right? If this is my electron or this is my psi, I can view, so what's the charge associated to the symmetry? What's the conservation law? What is conserved? Yeah, you're on the right track, correct. Electric charge, right? So the electric charge could not be created or destroyed. It means that the number of electrons is going to be preserved, or electric charge is preserved. So charge left is preserved, charge right is preserved. So this is a 4-dimensional thing, right? If you do something like this, you're applying a gauge transformation the same way to the left movers and right, left chirality or right chirality. What's the conservation law associated to this? Charge left plus charge right is conserved.
We're treating those as wide spinors.
Well, it's massless, so it is wild spinors. When you put e to the power of I alpha identity here, and e to the power of I alpha minus I alpha here, they're exponentiating that thing, right? What are you do? What's the conservation law associated to this? It's the difference between charges, Q left minus Q right. So the name for it is the following. The vector transformation is when it's a symmetry. So there are 2 U1 worth of symmetries. We consider it as the one that we often think of it as a vector transformation or the axial transformation. Vector is when both of them are treated the same. The corresponding charge is the sum of the charges, and axial is the one that's the difference of the charges. Right? Good. All right. I will go to 2 dimensions very soon so that things become ultra clear, but I want to go over the 4D first. So there are 2 conserved currents, the vector and the axial. if there is a mass term for the fermion, what does it look like? M psi, psi bar psi. Right? If you look at this mass term, what does this mass term do? The vector charge, the vector current is preserved classically. Quantum mechanically, the axial one is violated. There are two U1s. What this breaks is one of the U1s. Which U1 is broken? This mixes the left movers and right. Sorry, left chirality, left and right. It tells you that the left charge can turn into right charge, but the total charge is preserved. Right? So this is just a classically something you could derive, and I absolutely recommend it. Just do this. Right? It's just a simple calculation of nodal currents. Good. So when we say gauge invariance forbids masses for photons, sorry, for fermions, what do we mean? We mean axial gauge transformations, right? Because we don't want to deal with this, this is an explicit breaking of the symmetry. We don't want to deal with this. We're going to start with massless fermions. So both of them are classically preserved. We don't want any explicit violation of things. Classical anomaly is the statement that classically M psi is 0, so both of them are preserved, but quantum mechanically there should be right hand, this should be 0, remain 0. Quantum mechanically there has to be a new right hand side appearing here. Good. We're going to calculate that and see the physics of it. Good. We'll see that there will be a chiral anomaly for 4D massless fermions coupled to gauge fields. Here's what it is. I'm showing you the expression. Do you recognize? So this is field strength. So there are two copies of field strengths contracted with the antisymmetric tensor. Do you recognize this? From a couple of lectures ago, you should recognize this as a dual gauge field. This is the dual gauge and F. This is a term that's gauge invariant. We could have added this to the Lagrangian. We talked, this is a theta term. It's purely topological. The physics of it is E dot B. So what does that tell you? It tells you that physically, you should be looking for violations of the conservation of charge left minus charge right. Every time you put the theory in a background where there is electric field parallel to the magnetic field, because this has to be non-zero. There's a component of electric field and magnetic field that are parallel. That is where things go to hell. E dot B. Good. This is called the ABJ anomaly after Adler, Bell, Jakiv. And as I said, every time you have a setup where E dot B is non-zero, the number of particles minus the standard particles can change. We're going to come back to this in sound. But let's talk about two dimensions. So for simplicity, to get rid of a lot of these representation theory Lorentz group, it's helpful to go down to 1 plus 1 and talk about massless spinors in 1 plus 1. This is where everything is very, very obvious in your face. All right. So everyone's with me. Any questions about this? Sorry, I think as I said, left. I don't know if I said the left movers, right movers. If I said that, I didn't mean them. I meant left chirality, right chirality. The discussion was completely 4-dimensional up to here. When I go to 2 dimensions, it becomes left movers, right movers. I don't know. I might have misspoken. L and R over there refer to left chirality, right chirality. All right. Any questions? So in the remainder of this lecture, we're going to go down to 1 plus 1 dimensions, spinors, massless QED in 1 plus 1. It's a very, very simple theory. We're going to see what the physics of this anomaly is. We're going to calculate the right-hand side of del mu J. Good? J mu axial. We're going to calculate the right hand side of v as well as 0. Good. All right. If there are any questions at any point, ask. I'll be very explicit. So what's the Dirac algebra in 2 dimensions? What is the Dirac algebra? Clifford algebra. You need gamma mu, gamma nu that satisfy the following anti-commutator. This is minus 1, 1, right? So, and this mu and nu run from 0 to 1. So here's gamma 0. Here is gamma 1. So this is sigma y. This is I sigma x. Good. Depending on your convention, you might end up with different things here. What is gamma 5? Gamma 5 is gamma 0 times gamma 1. Whoops. What is going on here? Sorry, I don't know what happened. What is this? Okay. Gamma 5 is gamma 0, gamma 1. So it's this guy. Your fermions are going to be doublets, right? 2-dimensional, right? Because it's chiral, I'm going to call, so this is a projection to the, sorry. These are 1 plus minus gamma 5 divided by 2 are projections to the upper and lower modes, right? So now these are 2 by 2 matrices, so it's pretty straightforward to write down. This is these, oh, sorry. So P plus is this, minus this, right? So when you act, I'm going to write my psi as chi plus chi minus. P plus of psi projects to chi plus. P minus of it projects to chi minus. Good?
When did you say that left movers and right movers versus left chiral and right chirals? What is the difference between these?
So one of them was 4 dimensions.
So that is the
well. So far here, left and right is a question of chirality, right? But I'll actually show why left movers, right movers. Why in 2 dimensions? You'll see in a second. Left mover, left chirality moves in the left, left movers and right. You'll see. This so far I haven't said anything. It's just a statement about representation theory. Chirality is a statement about representation theory of spin half particles, right? All right, so what's the action? The action is I, Dirac action, massless Dirac, psi bar, del slash psi. So that is I, gamma dagger, gamma 0. What is del slash? It's gamma mu del mu. So it's minus gamma 0 dt plus gamma 1 del x psi. Is that clear? So let's expand this very explicitly. What is this? This I see chi plus star, chi minus star. This term is del t because gamma 0 times gamma 0 with a minus, just identity. And this term is del x minus del x. Oops, sorry. Good. So when you expand them, the action becomes chi plus star, del plus of chi plus del minus star, del minus of chi plus. You see clearly that they're decoupled. Right? Del plus and minus are. Now, what are the equations of motion? Tell me what are the equations of motion. What's the equation of motion for chi plus? I have to vary the Lagrangian with respect to chi plus. What do I get?
Chi minus, then minus.
So what's the solution to this? It means that chi plus is a function of x plus, sorry, x minus. Right?
What do you mean?
If chi plus, what is x minus? X minus is t plus x. Right? Plus x minus are t plus minus x. Right? So there are 2 degrees of freedom, t and x. I can repackage them as plus and minus. If this is the equation of motion of chi plus, it means that chi plus is a function of x minus. That's the solution. And if x minus is a function of only x plus, that's good. Now, what does this mean? It means that it's a left mover. And the other one is a right mover. It's a two-dimensional phenomenon. Right?
Wait, but it's x minus, so it should be t minus.
So, oh yeah, sorry, my notation, correct. So it's right mover. X plus is a right mover. Okay, sorry, thank you. Good. I had it correct here. So this is this is a left or right mover? I don't know. So X plus is a function of t minus X. Which one is left? Anyway, oh, this is a left mover. As t goes up, X has to X has to go up. Oh, so it's a right. Yeah. Okay. Never mind. Anyway, so one of them is left mover, the other one is right movers. Okay. The theory is made of two decoupled chiral modes: psi plus or chi plus, psi plus or psi minus, right? The notation here. Psi plus means chi plus 0. Psi minus 0. So every time I have psi plus and psi minus, there are two vectors. These guys are just functions. All right, there are two global symmetries. Is chi plus going to e to the power of I alpha chi plus, chi minus going to e to the power of I alpha prime chi minus. The conservation laws is, actually you said charge, so let's go with charge. The charge plus and charge minus are conserved. Charge density, right? What is charge density, by the way? J0. Right? Now, as we said, we're going to view the diagonal one as the vector transformation, the vector charge. That's plus charge plus minus charge. And then the other one is e to the power of I alpha gamma 5, right? That is conserved rho plus minus rho minus. Sorry, I think I wrote something incorrect before. E to the power of I alpha gamma 5 is this. E to the power of I alpha minus. I think I put the minus up there. That was incorrect. Good. So the global symmetry is clear what it is. So as we said, what we're going to see. Okay. Now, let's talk a little bit about these charge conservations. It's helpful to think of, to build intuition, it's helpful to think of Dirac C. So what do you have? You have a bunch of left movers, right movers, right? Here, and they're independent. They're completely independent. Their number, their charge or charges independently conserved. So here's the Dirac C here, here's the Dirac C here, right? They're filled. I'm just drawing them as discrete because you can think of this in finite volume in which momentum becomes discrete, but there's an infinite number of them, right? All right. So what do the excitations of this theory look like? Well, you could poke a hole and bring an excitation up here. That preserves charge. In the Dirac C picture, this is what the excitations are, right? Particle hole excitation. And this guy, you could remove a guy, put it here. What is forbidden by the axial charge conservation is that you cannot remove one from the left movers and put them in the right movers. That's not allowed. This would forbid is forbidden by the axial charge. So in anticipation for the fact that the axial charge is going to be violated, this is the setup you're going to be looking for. Good. Notice that why is this going to be important for us? Because as I said in Sano-Marlowe particle physics, we would like to have a theory that only has left chirality, not the right chirality. That's just the the model we write down that matches experiments. So to describe nature, we propose an action. There are a bunch of matter content I put in there. I calculate loop diagrams, everything. It has to match everything. If I put chiral fermions in my model, for the model, forget about nature. For the model to exist, to be sensible, not be garbage, you better have no chiral anomaly. Right? That's all we're talking about. It's the consistency of the model. Now, standard particle physics happens to have a chiral description, and that's important. Because otherwise, what happens is that quantum mechanically, you know that there must be the other chirality. It makes no sense to write just left chirality. Good? That theory doesn't make sense. So if it's not familiar that in standard model we have chiral fermions, it's good because you will see the standard model action. It's very important that you have chiral fermions. In fact, very good. If you have chiral fermions, you have a gauge group. So here there are two gauge groups in a sense. There are two U1s. There's U1 left times U1 right. When I talk about a theory with only chiral fermions left, for example, I'll write for my action U1 left. Right? So in standard model, we'll literally write that down. We'll have SU2 left. SU2 of SU2 standard model is left. It's not left right. It only acts on the left chirality. All right. So now let's take these fermions to be charged under electric field. Right? What is the action now? But I'm going to take this to be a background electric field. I don't even want the electric field to be dynamical. Right? These are electrons that I put on, like this lamp shift, right? You have an electron, you put in some background electric field. This is background. I don't even need to worry about the gauge action. Here's what my d mu is. Now there's a mu here. The electric. So I'm going to first describe it physically and see how the charge difference is violated, axial symmetry, axial charge is violated, and then we're going to do the calculation. All right. So these guys cannot be static. By the way, if you have only chiral theory, those charges cannot sit there. They just have to move with the speed of light, right? To have a particle that can be at rest, we should have left movers and right movers, left chirality and right chirality. Otherwise, these are massless modes. Photon cannot be, you cannot stop a photon, right? The photon is always moving with the speed of light. A massless fermion is always moving with the speed of light. So these guys, in any configuration you imagine, there are a bunch of particles that are moving in this direction with speed of light. So we're in 2 dimensions, right? Here's the picture. In 2 dimensions, this is X, right? There are a bunch of particles that are moving this way, and then there are a bunch of particles that are moving this way with speed of light. Now, imagine I introduce an electric field in this direction at time t equals 0. I turn it on. What does it do? These guys have charge Q, right? These guys have charge Q. It will accelerate these guys and will try to decelerate these guys. It will cause a delta P. How much is a delta P? The electric charge times electric field times T. Right? These are still massless modes. So what does it mean? It means that these guys were moving towards larger X. The P will increase. These guys were moving in this direction. The P's will decrease. So what I've achieved in the present, well, what has happened by turning on a background electric field is that all of a sudden the violated axial charge. This is only possible in an infinite dimensional theory. So here's a comment for you. If you think deeply about what is going on, if you take this analogy of Dirac literally, what is happening is that these are half infinite. So there's an infinite number of particles. You haven't really created, you brought them from infinity. Now, every time you regulate the theory, you're cutting this by finite amount. So we can't bring things from infinity, right? That's what's going on. The theory cannot be regulated. All right. So here's what it is again. Here's the vector current, right? Psi bar del mu psi. Here's the axial current, psi bar del mu gamma 5 psi. These are the transformations. The corresponding charges densities are these, right? Rho plus will increase by this much. Rho minus will decrease by this much. Rho dot of V is 0. So that's good. This is conserved. However, rho dot of A is E electric field divided by pi. Sorry, there's a T in there. There should be a T in there. Let me see. Maybe there's no T. I don't remember actually. Sorry, let's.
Two of those.
No,
That's all done.
no, it's oh, rho dot, right? Thank you. Yeah, no, the 2 is not there because I'm subtracting the 2, so this plus is minus.
All right.
Thank you. It's rho dot. It's rho dot. Good. So this is violated. All right, questions? So imagine mass, this is what I'm going to describe is very close to standard model. That's why make this comment. Imagine you have massless fermions and try to gauge only the left-handed ones. There will be, this is in the presence of axial anomaly, this is inconsistent. You can't do that, right? You can't have gauge transformations act only on left movers. That's what happens in a model that has chiral anomaly. Chiral gauge anomaly. Good. Standard model will not have this. Well, fermions of standard model will have chiral anomaly, but they cancel. When you have a bunch of terms, there will be a bunch of them that appearing, and the numbers you'll have to add and subtract them, and it will have to hit 0. And the matter content that people write down for standard model has exactly that cancellation. It's beautiful. It's a beautiful story. Good. All right, questions. This was the intuitive part, intuition building part. The rest is going to be calculations and directly calculating what the right-hand side of del mu j is. Good. By the way, what was del mu j mu in gauge theories? The fact that it was 0, we gave it a name. Yes, Ward-Diddins. So we're going to be calculating Ward-Diddins. Okay. Let's gauge the axial symmetry. We're in QED2. What we are after Fourier transform, this is Q mu, J A mu. We want to calculate this. A means axial. We'll see. It turns out that this as an operator is proportional to identity. It's topological. So yeah, I'm not explaining this yet, but let's just take this as an assumption, which means that if it's just proportional to identity, I can calculate the right-hand side of this if I just calculate the one-point function. Right? In principle, it could have been something more complicated, and the one-point function would not have given me the whole operator, right? Turns out in this case, for many reasons, it's true. So we're going to calculate this.
Sorry, why the fact that it is IDA proportional to identity allows us to just remain at one function?
Because it's identity times something. When you calculate the expectation value of the identity operator, what's the expectation value of the identity operator? 1. So that's something is well, if you have an operator, So del mu of J mu is an operator. Let's expand in terms of all the operators I have. There will be piece plus identity, there will be all sorts of other operators. When I calculate the 1-point function of this guy, I'm reading this piece. If the other operators have 1-point functions, what does it mean? A VEV for that. It means I'm spontaneously broken.
Right.
So, right, if I don't want spontaneous image breaking, I better only have this break. What I told you, not an argument. It's like a qualitative argument, but let's go with it for now. All right. There's a lot. Anomaly, you could spend 10 lectures on anomaly. It's a long story. All right. Okay, so how do I calculate this guy? If I want to calculate this guy, here's what this object is. And the piece that matters is the amputated part of this. It's just basically this loop thingy. And this is the same as the amputated part of the vacuum polarization. Right? Therefore, instead of doing a brand new integral, I'm just going to copy the vacuum polarization answer and then follow from there. All right? All right. Axial anomaly in 2 dimensions. Here's vacuum polarization. What was pi of q squared? We did dimreg. Thanks God. So I don't need to worry about dimensions. Here it is. This expression for it. Now, interestingly, previously there were divergences, right? Interestingly, in d equal 2, this is not singular. And as a matter of fact, when the mass of the fermion, so this is not singular, you could do the integral. When the mass of the fermion is 0, this is just 1 over q squared. So you obtain pi of mu nu q is minus e squared over pi, eta mu nu minus q nu over q squared. This is what pi mu nu is. Should you be concerned? As a calculation of vacuum polarization, what is this supposed to signify?
The mass, there is some mass.
This gives a mass to the photon. Is that bad? It's in principle bad, but not if you have a massless mode in your theory. Here we have massless fermions. So there is no violation, nothing is wrong. As a matter of fact, this answer, so there's a mass that's proportional to e squared over pi that we calculated one loop for the mass of the photon. QED2 is an exactly solvable model. You could calculate this non-perturbative, and the answer is this. So photons in 2 dimensions in QED, there's a mass, e squared over pi. This is consistent with ward identities because as we saw in spontaneous symmetry breaking, if you have massless modes, that's just perfectly fine. And here we have massless modes, fermions. Chiral fermions, right? It has to do with the fact that there's a pole at q squared equals 0. The electron positron running in the loop. All right, questions? Okay, so here is what I want to calculate is this guy. So let's just write it in Fourier space. Integral of d2 of x, e to the power by qx, j nu vector anomaly. Let's first do vector anomaly. This is minus I over e pi mu nu a nu. Pi mu nu is the thing that we just calculated, right? It's just basically this coupled to this guy. All right, so this we calculated, this e over pi, this expression, e squared over pi, but there's an e downstairs. So you end up with this expression. Q mu acting on this gives you 0. That's good. You could have guessed it's transverse. Everything is good. This is for the vector current. What about the axial one? In d equal 2, you have this funny, well, interesting identity that gamma 5 gamma mu is epsilon mu nu gamma nu. Axial current had gamma 5 gamma nu, So you could write this relates the axial current to the vector current using this identity. So I don't need to do a new calculation. I recycle the old calculation. So it's basically the previous answer contracted with an epsilon tensor. All right, put an epsilon tensor here. This is what you find. Now you're in trouble. Can you see it? Well, because of this epsilon mu nu, the right-hand side no longer vanishes. So what is the right-hand side? You can calculate it. It's just epsilon mu nu, f mu nu, identity minus e over 2 pi. We have an anomalous axial ward identity in the equal 2 dimensions. There exist no regulators that can preserve both the axial current and the vector current. So JA is not conserved. Its corresponding charge is not conserved. Good. I'm running really behind. Are there any questions? All right. If the class, well, so what is the physics of anomaly? I said this at the beginning. If the classical action is invariant under symmetry, how could anomalies arise? They could arise. The only thing it could be is that the measure is not invariant. Can we use this to calculate what we just calculated? Can we calculate the chiral anomaly using path integrals? The answer is yes, and we're going to do it hopefully the remaining time. This is called the Fujikawa method. Okay. So here's the transformation for the axial. This is the axial transformation for psi and psi bar. I write them explicitly. Do you know why? Because the path integral is the path integral over psi and psi bar. There are 2 degrees of freedom, right? 2 modes. Here's the action. Let's not put a mass term. So this is all you're dealing with. Under gauge transformation, this is what it changes with. You use integration by parts, you put it on del mu, and you get 0. Right? So if mass is equal to 0, you have classical symmetry. That will not survive quantum mechanics. The first thing to notice here is that I use integration by parts. Well, this is actually relevant for the next few lectures, but not today. But just keep in mind that I get gauge invariance when my boundary is all the way to infinity and the field vanishes there. I use integration by parts. If I bring the boundary in a finite distance, gauge invariance is not true. Right? This is an important story. It's a story of edge modes. But I don't want to get into physics of it. I just want to make this observation. We'll talk about the physics of it later. Good. Alrighty. Here's a path integral. D psi bar, e to the power of I psi, S psi. So what are psi and psi bar? These are fermion modes. The action is psi, d psi bar, d slash psi. So if I solve the Dirac equation, the eigenfunctions of the Dirac equation. So I find the eigenfunctions of the Dirac equation. These are a bunch of Gaussian integrals, and the eigenvalues are the only thing I care about. Right? So these are the eigenfunctions of phi. These are the eigenvalues of them. Good. So now the way I can view this is that I can take my psi and expand it in a complete basis of the eigenfunctions. These are AMs. These are path integrals, a bunch of integrals over AMs. AMs and AM primes, right? These are Grossman variables. Why? Because this is a fermionic field, and these are just eigenfunctions of the Dirac field, right? So these are Grossman variables. That's why the path integral will give you determinants, not inverse determinants. Now, under an axial transformation, the measure transforms by this Jacobian J2, 1 over J2 of d psi bar. we're going to calculate that. Okay, psi transforms in the, you know how psi transforms, so we want to calculate how this transforms. So what is AM? We're path integrating over, you're integrating over AMs. M are the labels for the, yeah. M is infinite number, there are infinite number of M's, right? So psi of X transforms as infinitesimally as 1 plus I alpha gamma 5 psi X. That's the infinitesimal transformation, which means that A of M transform goes to AM plus an integral of 5 bar I alpha gamma 5 psi of X. Right? This could be re-expanded in terms, so A of M goes to A of M plus sum over N A N C M N. This is CMN. Integral over phi M alpha phi N. So what does this mean? It means that a gauge transformation written in this basis mixes them. There's a matrix in this basis. It's just a matrix. It's the same thing when we write the determinant of a differential operator. That's what we're thinking of, right? The differential operator will have a bunch of eigenvectors, right? And you view it as a matrix in that language. It's the same thing. So that's what we're calculating. Sorry, I'll go 5 minutes over time. So under an infinitesimal gauge transformation, pi of M AM goes to pi of M 1 plus C M N AM. This is a matrix. The Jacobian, there will be we'll pick up a Jacobian. What is it? It's just determinant of 1 plus C. All right. Determinant of 1 plus C, right? There's the exponential of trace of log of identity plus C. Is this clear why? Okay. If C is small, this is just exponential of trace of C. There's a small coefficient in front of it. What is a small coefficient? A small gauge transformation, because alpha sat there. Right? But this is just a trick. I in principle, you could calculate these brute force. It's a free theory after all. You could calculate. I'm just trying to simplify my calculations. So what is trace of C? It's an I integral of alpha of X sum over N phi N bar of X gamma phi phi of X. This is the expression we have. Good. This trace is infinite. What we would like to do is to regulate it. Good. But this is the Jacobian we're picking up. All right, how we're going to regulate this? This is the part that is important. We're going to introduce e to the power of lambda n squared, because lambda n's are negative. Lambda n squared are negative over m squared.
Where m squared is
a large parameter. It's a regulator. Right? You have an infinite sum. What you want to do is you want to, this blows up because as n gets larger and larger, these numbers are not small. You exponentially suppress the large ones. You're regulating this, right? And you introduce some sort of mass parameter. It's not mass, sorry, it is a kind of mass. Good. Now the shocking statement is that when you take this limit, things will work out to give you an order 1 expression. We'll see. All right. So here's what we're calculating. I put eigenvalues, but now these are eigenvectors, so I can just put explicitly what the operator is. It's just Dirac operator squared. If you remember Dirac operator squared. Good. What this is the limit of m going to infinity of trace of gamma 5 e to the power of this thing. You might have thought that limit of m going to infinity of this sends m to infinity. You're left with trace of gamma 5. That's infinite, and you just bring it out of the action. That would be incorrect. This is very important. Let's skip this because I don't have time. It's just like explaining why. Well, maybe not. No, I don't think I can skip this. Woo. Okay, 5 more minutes. Sorry about that. So what is d slash squared? is minus gamma mu d mu d nu, right? Using the commutator of gamma mu and gamma nu, you could write it in terms of the representation of the Lorentz group, right? And d mu d nu, which gives you this d slash squared in terms of just good old d squared plus a term which is proportional to f mu nu. Good. Notice that f mu nu is up here. So you first see the appearance of f mu nu here, but still naively you would have thought as we send m to infinity, this term is irrelevant. Good. Is this clear? It's kind of like magical that this will have a constant piece. Do you have a guess as actually what's going on?
The second term is like the annual return of the del mu j.
So there are no. Well, it is, yes, but why is this giving you a finite piece? That's what I'm asking. You might have expected. So what is this? It's sort of like a correction to something infinite, right? That's what's going on. So let's expand this. So exponential of this thing, we're going to expand it. We're going to get trace of gamma 5, 1 minus d squared over m squared plus e over 2m squared del mu f mu nu plus da. All right. So in d equal 2, trace of gamma 5 is 0. So this term goes away. Trace of gamma 5 sigma mu nu is epsilon mu nu. Right? So as you can actually, as expand these, you could see that you could repackage using the fact that gamma 5 trace of vanishes, you could repackage this bunch of their terms in terms of this expression. Good. Now, can you see what is going on? There is 1 over m squared, that this thing goes to 0. And this goes to 1. So now you would have thought that this just goes away. This term goes away. But now this trace is infinite. All right. So this trace means what? It means over space time. So let's calculate these. Take the log of j, bring this out. It's minus e over m squared, epsilon mu nu, f mu nu, alpha. I'm taking alpha to be, integral of d2 of k e to minus k squared over m squared. Okay, that's just this term. And integrating over. All right. Now, this expression, you see what's going on? Integral of dk e to minus k squared over m squared is m to the power of d. So if you look at this expression, you would have said m going to infinity. Yeah. No, well, you would have said m going to infinity gives 0 here, right? And this piece is infinite. But what is important is that in 2 dimensions, md appears here, which means that m2 appears here, and that m2 cancels this m2. That's the point. So this is infinite, exactly the same amount that will cancel this. So once the dust settles, I'm sorry that I rushed it, you find that this Jacobian is e to the power of I e over 2 pi integral of alpha of x epsilon mu nu f mu nu, because f mu nu is the only thing that matters here, the only piece that remains. So this is the right-hand side of your calculator, your excellent number. I'll repeat this calculation in 4 dimensions next time. Okay, I rushed towards the end, so sorry about going over time. Are there any questions?